Welcome back to ECE 220. Today is the beginning of labs. Lab 0 begins for one of the sections. Don't ask me which one. Is it E? Section E, I believe, today. And there's 3 things you need to keep track of or to do relative to that. And I was reminded as I was walking down the 3rd floor hallway by the hall monitor, somebody was caught without closed-toed shoes. So please wear closed-toed shoes if you're going into the lab. Bring your CAT card and bring something to take notes with. And that begins today for one of the sections. The remaining, or the other 3 sections, will have it on Wednesday, Thursday, and Friday, and then Group B, which is Section I, will have it next Tuesday, their orientation lab. Homework 2 is due today. P-Spice, that homework assignment, if you don't want to put it on your own machine, you can work the P-Spice. You should be able to in room ECE 232. They should have P-Spice loaded on those machines. That homework assignment is due in class on Friday of this week. Homeworks 3 and 4 will actually occur before the exam. Exam 1, if you want practice material, look on D2L for that link. And today what I want to do is get into measuring voltage and current. How does that occur in the lab? I should have brought a meter with me and had it on display as we talk, but we'll talk about a D'Arsonval meter and how that is now incorporated into both a voltmeter or an ammeter in a multimeter device. How can you, or how do we utilize one meter element into a device that can be used for multiple measurements? So we'll look at measuring voltage with a voltmeter, the ideal meter instruments, and then we'll come back to reality and say, okay, what's actually happening with a real analog meter? We'll create more universal instruments by introducing external resistors to the D'Arsonval meter itself, and then that whole package would be considered a voltmeter or a ammeter. The combination of these external resistors with the meter, the D'Arsonval meter movement, and then we'll look at 2 different ammeter ranges as far as selecting those additional resistors. Here's a schematic diagram of a D'Arsonval movement. Essentially, you pass current through this coil, and it's inside or located around or near this permanent magnet, and the interaction of that magnetic field with the field generated by the moving current in that coil causes this needle or dial to move according to how much current is passing through that coil. That's the idea. Here's how you will see that physically in the lab. That's why I was on the 3rd floor yesterday. I was taking pictures of what you will be seeing in the lab, and here is that meter that you will be using to take particular measurements, and you can see that there's a positive and a negative terminal that you will put the banana jacks in, or the leads that have banana jacks to them, in order to use this meter as an ammeter or as a voltmeter. I went ahead and just pushed it a little bit to full scale. We'll talk about full scale reading. Hopefully you can see that the red needle is now over to the 1 milliamp setting on that dial. And that's what would happen then if we wanted to push this to the limit or to its FSR or its full scale reading. Suppose now we wanted to measure a voltage with a voltmeter. And now this voltmeter could be just a handheld device. You will have it as an instrument on the bench that's the multimeter, and you'll now set it up to where it will be functioning as a voltmeter. Here I have it schematically drawn as just this box. It has one lead going to, I'm saying, the positive side of resistor R sub 2, and another lead going to the lower side of R sub 2, or the negative lead. And you might then connect that to voltage and common on your instrument. And this little round circle is a knob that you can adjust. If this is a multimeter, now you can adjust it to measure voltage. Maybe it will measure current as an ammeter, and it will probably measure ohms or resistance as an ohm meter. That's why it's called a multimeter. It can function in many different forms. If we're now measuring this voltage, what do we expect to see for V sub 2? What is V sub 2? Do you have a way of determining what you would expect V sub 2 to be? Yes? So now if we're asking what is V sub 2, the result is, isn't it, using the voltage divider, isn't it V sub 2 equal to R sub 2 over R1 plus R sub 2 times the source voltage V sub S? And you've probably heard the adage, you can't get something for nothing. We're actually measuring this, so what are we doing? We're inserting something across that resistor, and what is that something behaving like? Probably another resistor. So now we have this loaded resistor effect. So unless that voltmeter is ideal, we wouldn't get exactly this V sub 2 value out of that instrument. This voltmeter then is acting like we're putting another resistor in parallel with that resistor that we're trying to measure, which is R sub 2. So I would say, isn't it V2 by the voltage divider? And in fact, I would say it depends, because the voltmeter itself will actually load R sub 2 and influence the measurement. If we could figure out what that voltmeter looked like in terms of a resistance, if we could say, oh, that voltmeter appears as if it's a resistance of value R meter, for example, let's say that the voltmeter can be modeled as R meter. Now what would the formula for V sub 2 be? Now R sub 2 has been joined, so now there's a party going on. R sub 2 and R meter are in parallel. R sub 2 hat is now the parallel combination of R sub 2 with R meter, and then you could go back to what you know. you now know that V sub 2 is R sub 2 hat using our generic voltage divider formula, but now that R sub 2 has been modified because it's loaded by the meter's resistance, where I'm calling R sub 2 hat the parallel combination of R sub 2 and R meter, or the resistance of the meter. What if we go back to the ideal scenario? And in this configuration, we have an R1 and an R2 in series with this voltage source, V sub S. And now we've installed, or we're measuring, two different parameters or variables in that circuit. We're measuring current through that ammeter. That has to now be placed in series with whatever current we're trying to measure. And we're measuring the voltage across R sub 2, and that we then say we're putting leads across a resistor in order to measure the voltage across that resistor. If I had an ideal ammeter, what would that ammeter present, or what would it look like to the rest of the circuit if it's ideal? If you want an ideal ammeter and it's in series with R1 and R2, you hope that in order for it to disappear, it needs to look just like a wire, doesn't it? It needs to look like a short. That ammeter then, for an ideal ammeter, that's a short circuit. Or it appears to be 0 ohms. That means that that ammeter causes no voltage drop. We're in the ideal scenario, and so now that ammeter, if it's ideal, looks just like a wire. And that means that there's not going to be any voltage dropped across it. What about the voltmeter? If it is ideal, what does it appear to do relative to the rest of the circuit? What does it look like? If essentially you want R sub 2 to disappear, if you want the voltmeter to disappear relative to the rest of the circuit, what does that voltmeter need to look like or be? It needs to be open, doesn't it? It needs to be an open circuit, or how much impedance? Infinite. So now for an ideal voltmeter, we need that to look like an open circuit, or an infinite impedance, and that scenario then would allow that voltmeter to draw no current from the rest of the circuit, because it looks like an infinite impedance. No current's going to flow to an infinite impedance. So this draws no current. That's the ideal scenario. But unfortunately, we don't live in an ideal world, but we try to make it as ideal as possible. So we want to try to make this ammeter look like a wire when we have it acting as an ammeter, and we want this to look like a open circuit when we have a voltage measurement that we're trying to perform. And the way that we're going to make these measurements is by using this instrument, or this meter movement. We're going to pass a current through this coil. The interaction of that current sets up a magnetic field of its own, but it's sitting inside a permanent magnet, so that has a magnetic field. It's going to deflect that needle. All of that going on really says that we can model that electrically in the following way. We can replace that D'Arsonval meter movement with this schematic. It can have a resistor, R sub M, That's the internal meter resistance, and hopefully that is small if we're now measuring current. And this dial is ideal. It's just going to deflect. But it's going to be limited. There's a full-scale deflection in that movement, and because of that we're going to have to restrict our current through that to be little I sub m. That's going to be the current required to produce that full-scale reading. And if we have an I sub m and an R sub m, Ohm's law tells us what V sub m is going to be. V sub m is going to be the voltage corresponding to that full-scale reading. These are the variables or the notation that we're going to use in our discussion for creating voltmeters and ammeters by using this D'Arsonval meter movement. We'll have this little piece, this electrical piece, in combination with something else so that we can actually build with this one device a voltmeter or an ammeter. If you go into the lab and look to see what's going to happen if you now applied, or I essentially now just tried to measure the resistance of that picture of the D'Arsonval meter movement that I showed earlier today. And I measured 163 ohms. And the full-scale reading is 1 milliamp, so that gives me a V sub m of 163 milliamps, roughly. It was 162.7 or something, ... If that's the case, are we forced to always try to have 1 milliamp flowing or 163 millivolts appearing whenever we try to use this meter? Do all of our circuits operate with full-scale readings of 1 milliamp and 163 millivolts? What do you think? Life would be pretty boring, wouldn't it, if everything revolved around 1 milliamp? We wouldn't be doing too much with that. So, in order to make this meter more applicable to a larger environment, we need to modify things, and for that we're going to need to introduce some resistors to make, let's say, a given, because you could have different full-scale reading currents or voltages for a given meter. We need to introduce resistors to make a given D'Arsonval movement more universal. For example, if we wanted to have maybe a full-scale reading of 100 volts, not 100 millivolts, maybe 100 volts, do you see that we could maybe put in series with that electrical schematic of our D'Arsonval movement another resistor R sub V? And if we make that big enough, then the total voltage drop across those voltmeter terminals will be 100 volts when the current flowing through that series combination is 1 milliamp. That's how we could build a voltmeter with that original D'Arsonval movement. Or, if we wanted to measure current, now we know how current dividers work. We would just put another resistor in parallel with that electrical schematic and divert most of the current through R sub A and have 1 milliamp flowing through the d'Arsenval movement, even when maybe 2 amps is going into the ammeter itself. The blue box is saying these are the terminals of your ammeter. Internal to that, you might have a knob and you're putting in place different resistors. Here you're putting in an R sub A in parallel with that d'Arsenval movement. Up above, when we were measuring voltage, we're now putting bigger resistors in series with that d'Arsenval movement. What we now want to do is figure out how do we select the R sub V's or the R sub A's for a given circuit or variables that we want to measure. That's our task now. So let's now select R sub V in a voltmeter. Suppose we have this different selection available by a switch of resistors. And that's now in series. That's the R sub V. It's in series with this electrical schematic of our d'Arsenval meter movement, which we said we're modeling as a small resistor and an ideal meter. And that small resistor then is going to be consistent with whatever the full-scale reading of that meter is in current and voltage. So let's now create a design equation for R sub V based on somebody telling us what voltage blue B they want to have measured. Now they say, oh, I want to have a full-scale reading of 100 volts. And you know maybe your d'Arsenval meter only measures full scale of 100 millivolts. That's quite a difference. But can we design an R sub V to allow us to connect the leads of this voltmeter across 100 volts and have that meter movement accurately move proportional to the voltage it's measuring? Little I sub m is the current that gives full-scale reading in that meter movement. What if we now followed this yellow highlight as a KVL equation? Can we write a KVL equation? Now we're assuming that switch is now connected to that top resistor, and that top resistor we're labeling as R sub V. We now want to measure V, and in this KVL we'll say, okay, it's minus V, then how much current is going to be flowing through R sub V for full-scale reading? How much are we going to see? What's the current flowing through R sub V to have a full-scale reading on that dial? Is there a variable on the screen that you could say, oh, I know what the current is flowing through R sub V for full-scale reading? Isn't it I sub m? So I sub m is going to be going through R sub V. It's going to be going through R sub m, the resistance of the meter itself, and then it'll flow back to where we started. So we have two resistors that current is passing through, and we have our voltage associated with the location in our circuit that we're trying to measure voltage with respect to. The KVL is then minus V plus R sub V I sub m plus R sub m I sub m equals 0. We're trying to find a formula for R sub V. And everything else in that equation is known. If we know the full-scale reading current, I sub m, if we know the full-scale voltage reading of that meter, V sub m, we can calculate R sub m. We know V, the full-scale reading voltage we want to have measured with our voltmeter. The only unknown is R sub v, so let's now solve for R sub v. We now have R sub v I sub m is equal to v minus R sub m I sub m. Or our formula now, the design formula for this series resistor to build our voltmeter, R sub v is v minus R sub m I sub m over I sub m. This voltage is given because we know what we want to measure, to be measured. I sub m is from our d'Arsonval meter, that's a given parameter. As is indirectly, if it's not given directly, R sub m. And if we wanted to, we could actually rewrite that and say this is v over I sub m minus R sub m. Another way of writing that design equation for R sub v. Suppose, let's look at an example. Suppose we want a full-scale reading when we measure, or with V equal to 100 volts. That's what we want to be able to measure with this meter. And suppose that we have a d'Arsonval meter movement that has a maximum voltage dropped across it of 100 millivolts when we pass through it a current of 1 milliamp. This is given information from the meter. You'd buy a meter off of the internet, and it now has particular specs, and those specs will be given by the full-scale reading of your current and voltage across and through that meter. If that's the case, can you tell me what R sub m is? What's the internal resistance of that meter movement? If it's governed by V sub m and I sub m, we know Ohm's law. This is just V sub m over I sub m, or this is now 100 ohms. If that's the case, what is R sub v? In order to get full-scale reading from a 100-volt measurement, we now say that that's V over I sub m minus R sub m. V was 100, I sub m was 0.001 minus 100 ohms. Or this is now 100,000 minus 100 or it's now 99,900 ohms is R sub v. And that's what we would then need to connect up with our d'Arsonval movement. If we wanted to build that voltmeter, we would now put in series this 99.9K with our meter in the lab. And now we're set to measure 100 volts across. This is, in fact, the effective voltmeter that I now have highlighted in the dashed red box. Yes? So now the question was, in an actual voltmeter, we have ranges, or that switch that's typically on the voltmeter is clicked, and that's really switching in a different R sub V to give you a different range of voltages. So you want that meter movement. If you knew you were measuring up to 2 volts in the lab, you probably wouldn't want the full scale reading to be 100. You would say, oh, let's go from 0 to 5. So now you dial that switch to give you a full scale reading of 5 volts, and now you get a better deflection and a more accurate reading.
So is it basically a resistor that would be treated as if it was going to be 5 volts?
So now,
Less than 5?
yes, so now if you knew that you were going to be measuring somewhere in the range of 2 volts and your meter only gave you certain possibilities for scales, it may give you 0 to 5, 0 to 100, 0 to 1,000. Now you have different R sub V's for each of those settings. And when you turn the dial, you're effectively switching between those R sub V values. That's what you're doing in this analog voltmeter. What if we wanted to create an ammeter? Now instead of a voltage divider scenario, now we have a current divider scenario. Now we have this collection of resistors that are going to be introduced in parallel with our default d'Arsenval meter movement. And where we dial that is obviously going to be determined by what we anticipate the current being. What do? You usually start at the biggest range, and then you go, whoa, the needle hardly deflected. I think I can go to the next smaller range. Oh, now the needle deflected 60% of the way. Oh, I better not go any smaller in my range of current or voltage that I'm measuring. In this scenario, we're trying to find or solve for R sub A. We have a current that we want to measure, that's little I, and that current, depending on where the switch is going to be divided among 2 different resistors. An R sub M, which is the resistance of our meter movement, and an R sub A, which is set by the selector switch on our ammeter. Here we're just going to call it R sub A. But in reality, you would have an R sub A sub 1 and R sub A sub 2, depending on the different ranges. I hope you can see that we're really just doing a KCL at that node. I comes in, and it gets divided. Part of it goes through I sub A, and the other part is indicated by I sub M, and it's going through R sub little m. So let's now figure out what that looks like by applying current division. What is I sub A? Current division formula-wise. We take the opposite resistor, and that's what's upstairs or in the numerator, and we divide by the sum of the 2 resistors that are in parallel. We're dividing by R sub M plus R sub A. What's in the numerator if we want an expression for, what did I want first? I sub A. We're trying to shunt current, most of the current, through I sub A, because our little meter movement can only maybe tolerate 1 milliamp. So most of the current we want to throw through R sub A. what's the formula for that shunt current I sub A? Shunt just means we're shunting it down. Isn't it little, or R sub little m over the sum of those two? If you had the notes, you knew that already, right? What is little I sub m? It's just the other version. That's now R sub capital A over R sub m plus R sub A. And now what we want to do is solve this for the unknown shunt resistor R sub A. That's the formula that we want to now use. We know I sub m, that's based on our meter movement. We know R sub m, that's a part of our meter movement. We know what the current is that we want to measure, that's little I. The only unknown is R sub A. Now we just need to do some algebra. If we multiply both sides through by the denominator, we end up with that. Or R sub m I sub m is now equal to R sub A times I minus I sub m. And now we're in a position to solve for R sub A, which is what we wanted. R sub A is now R sub m I sub m over I minus I sub m. Or you could write that as, using Ohm's law, we know the voltage of our full-scale reading is V sub m divided by I minus I sub m. V sub m is given, as is I sub m. That's the full-scale reading of our meter, both of those. I is our desired full-scale reading of the ammeter, and the ammeter is the schematic that is identified by the red dashed border. The ammeter includes this series of shunt resistors together with the D'Arsenval movement. That combination gives us our ammeter. Let's now work the following. Suppose we want to design our ammeter by the choice of selecting this shunt resistor R sub A in order for the full-scale current to be either 2 amps or 50 milliamps when we have this configuration. This is our ammeter, where R sub A is in parallel with our given D'Arsenval meter movement. What's our formula for R sub A? That we just derived or found. That was V sub m over I minus I sub m. And we have most of that information here, or all of that. So now we have our formula. For R sub A, that's R sub A is V sub m over I minus I sub m. V sub m was 100 millivolts, or 0.1 volts. I in part A was 2 amps. I sub m was 2 milliamps. Keeping all of our units consistent. Now R sub A is going to be 0.1 divided by 1.998. Or, dividing that out, we end up with 0.05. It's a little bit bigger than 50 milliohms. 50.05 milliohms for part A. That's what the shunt resistor needs to be. It needs to be pretty small in order to pass most of that 2 amps through it and only 2 milliamps through the R sub m. So the majority of your current is going to be going through R sub A, which is 50 milliohms. What about B? What if we now looked at the second case where now we're wanting a full scale reading of that ammeter when we have I. Here is our I coming in. We want I to be 50 milliamps. We use the same formula, it's just now I is different. R sub A is now 0.1, or V sub m, let me just go ahead and write the formula. V sub m, I minus I sub m. We have 0.1. This is now 0.05 minus 0.002. Or R sub A is now a little bit bigger than 2. We didn't need to have as much current, or we weren't asking our meter to measure as large of a current this time, so that means that our resistance can be bigger to shunt the necessary current away from the D'Arsonval meter, which could only accommodate 2 milliamps. What's an observation? As the full scale reading of this current increases, in this case, we're increasing current from B to A. What happened to the shunt resistor's value? As we increased current, what happened to the shunt resistor? It went from 2 to 0.05. So the current went from 50 milliamps to 2,000 milliamps, and our resistor went from 2 to 0.05. So as the current increases, our resistance, or then R sub A, decreases. Let's look at another example. Suppose now we have a 2 amp source and it sees that circuit. What's the current I1 through that rightmost resistor? This is a very challenging problem. We have 2 equal resistors and they're splitting, or they're dividing a particular current of 2. So we split 2. The first half goes down the one, the other half goes down the other one. So I1 is 1. What if we now put a ammeter into that and we were trying to measure that? Suppose now we wanted to take this and put it into an ammeter. And suppose somebody gives you the following information about that ammeter. Suppose they give you actually a schematic. Maybe they draw this for you. And they say that R sub A is 100.1 milliohms. That's R sub A. And they say that this d'Arsenval movement has full-scale reading of 100 millivolts and 1 milliamp. All of this in the red box is our ammeter. What might we want to do first relative to this information about the characteristics of our ammeter? This is now going to be inserted between these 2 points. It's going to be in series, and this is what we're going to put in series. A parallel combination, essentially, of 2 resistors. But we need to find out what that R sub little m resistor's value is. Do we have enough information to do that? Feel like I'm dying here. In 2 different ways, with audio and with the audience. Can you now find R sub m from that information? V sub m over I sub m? What's R sub m? That's just 100 ohms. If that's the case, what does this meter look like as a resistor, effectively? What's our meter? Can you give me a formula or a description of what the resistance of the meter will be? Isn't it just the parallel combination of R sub A and R sub little m? That's our meter. This is now R sub A in parallel with R sub m. And that ends up being 100 times, whoops, that was in milliohms, so this is now 0.1001 over 100 plus 0.1001. Do you see that the hundreds in the numerator and denominator effectively cancel, and the resistance of the meter is 0.1 ohms? If that's the case, what is the actual I sub 1 in this circuit? Can you write down the formula? Isn't it a current divider? I sub 1 is going to be divided, or it's a part of the divided current that 2 amps source is giving us. What's the resistance in the branch associated with I sub 1? Well, that's just the series combination of the ammeter, which we said has a resistance of the meter of 0.1, and the 1 ohm. So that's going to be in the denominator of our current divider formula. In the numerator, it's just the resistance of the other branch, and that was 1. Or this is now 1 over 2.1 times 2. And that now says that the current is actually 0.952 amps. And what was the ideal current? Or if we had an ideal ammeter, I sub 1 would be, if it was a wire, then that 0.1 would be gone in the denominator and we would have 1 amp. Now do you see your percent error? It's going to be the I1 actual minus I1 ideal over I1 ideal times 100%. We'll try to summarize Chapter 3 next time, but now we have all the pieces and parts.